Let's look at section 7.3 where we look at rational exponents. So when we have a rational exponent of the form a to the 1 over n, so this is an exponential expression whose exponent is 1 over n. As long as n is an integer bigger than or equal to 2 and the nth root of a is a real number, then a to the 1 over n is the same as the nth root of a. Now when we go to talk about, so this is a rational exponent whose numerator is 1. We also need a definition for rational exponents whose numerators are not 1. So if m and n are integers and n is bigger than or equal to 2 and the nth root of a is a real number, then a to the m over n power is the nth root of a raised to the nth power. Or it could also be written as the nth root of a to the m. So this is going to allow us to work on problems in this section and to deal with radicals in a different way. So let's use this definition to rewrite 16 to the 1/2 as the square root. So the denominator of the radical is 2. That lets me know I'm dealing with a radical whose index is 2. That's a square root. So this is the square root of 16, which equals 4. Negative 8 raised to the 1/3 power, remember the denominator of the fractional exponent tells me the index of the radical, is the cube root of negative 8. The grouping around the negative 8 tells me negative 8 is the radicand because the power 1/3 applies to the 8 and the negative. So this is negative 2. 3 to the 2/3 raised to the 3rd power is actually the cube root of 3 squared cubed. Well, this is the cube root of the cube, so I can bring this power of 3 on the outside inside the radical. So this is the cube root of the cube of 3 squared. So the cube root and the power of 3 eliminate each other, and I'm left with 3 squared, which is 9. Negative 27 to the 2/3, the way this is written, the negative is not raised to the 2/3 power, only the 27. So this is a negative 1 times the cube root of negative 27. And that radical gets cubed. Squared. Notice the negative sign is still outside of this because anything having to do with that power of 2/3 only applies to the 27. So notice the negative is not inside the radical, only the 27. So this is negative, so the cube root of 27 is 3. So I square 3 and then multiply it by negative 1. So this is negative 9. Negative 81 to the 3/4, because of the grouping, the denominator tells me this is a 4th root. The 81 is the radicand. And then this will be raised to the 3rd power. The problem is this is not a real number because the index is even and the radicand is negative. So this is not a real number. So we won't do anything with this. A little bit later we'll talk about what kind of number this is. X to the 1/2 to the 2/3 is x to the 1/2 times 2/3, which is x to the 1/3, which is the cube root of x. X to the 1/3 times x to the 1/6 is x to the 1/3 plus 1/6. I need a common denominator to add these exponents. So I'm going to multiply numerator and denominator 1/3 by 2 to get 2/6. So the power on x is 2/6 plus 1/6, which is x to the 3/6, which reduces, the power on x reduces to 1/2. So this is the square root of x. 16 to the negative 3/4 is 1 over 16 to the 3/4, which is 1 over the 4th root of 16 cubed. Which is 1 over 2 cubed, which is 1/8. When I apply the power of 1/3 to 7x squared y, because that's grouped in a parenthesis, the power applies to the 7, the x squared, and the y. The denominator of that fractional exponent tells me this is a cube root, and inside the cube root goes 7x squared y. And I can't simplify that or break that down in any way. 32 to the 1/5 is actually the 5th root of 32. And this is raised to the 3rd power. So this is really 2. The 5th root of 32 is 2. This is 2 cubed, which is 8. 2 cubed to the negative 1 is 2 to the 3 times negative 1 power, which is 2 to the negative 3, which is 1 over 2 cubed, which is 1 over 8. Two to the 1/2 times 2 to the negative 5/2 is actually the square root of 2 over the square root of 2 to the 5th. This is another way you can look at this problem. So the rules of exponents tell me that I can make one square root and divide 2 by 2 to the 5th. The rules of exponents tell me 2 over 2 to the 5th is 1 over 2 to the 4th. So that 1, 2 in the numerator divides out with one of the 2's in the denominator, leaving me 4 2's in the denominator. So this is the square root of 1 over 2 to the 4th, which is 1 over 2 squared, which is 1 over 4. So I'm looking at that a little differently than I looked at it in class. And I'm actually using the quotient rule of radicals, which we have seen before and we'll review again in a moment. X to the 3/4 to the negative fourth is the fourth root of x cubed to the negative 4. Which is 1 over the fourth root of x cubed to the fourth. So if I move this to the denominator, that exponent of negative 4 changes to a 4. So this fourth power and this fourth root cancel each other out, and I'm left with 1 over x cubed, which is my final answer. When I raise a fraction to a negative exponent, if I invert the fraction, the exponent changes sign. So this becomes a positive power of 3/4 when I invert the fraction. And so this is really a fourth root applied to 625 over 2,401, which is then raised to the third power. Well, the fourth root of 625 is 5, and the fourth root of 2,401 is 7. So 5 over 7 is what I'm actually raising to the third power. 5 cubed is 125. 7 cubed is 343. So that's my final answer on this one. Okay, now we're going to use rational exponents to simplify radical expressions. So we're going to work in the opposite direction. We're going to convert each radical expression to an exponential expression with rational exponents. We're going to simplify by writing fractions in lowest terms or using the rules of exponents as the problem requires. And then we're going to convert any remaining rational exponents back to radical expressions. So this problem is going to be written as x to the 3 over 7 times x to the 1/6, which the rules of exponents say is x to the 3/7 plus 1/6. Common denominator is 42. I'll multiply 3 over 7 times 6 over 6 to get 18 over 42. And I'll multiply 1 over 6 times 7 over 7 to get 7 over 42. So this is x to the 25 over 42, which is the 42nd root of x to the power of 25. 15th root of x to the 5th is x to the 5 over 15, which reduces to x to the 1/3, which is the cube root of x. The 8th root of 16 is the 8th root of 2 to the 4th, and 16 equals 2 to the 4th. This is 2 to the 4 over 8 power, which is 2 to the 1/2 power, which is the square root of 2. Now let's look at the product rule for radicals, which we used earlier. If the nth root of A and the nth root of B are real numbers, then the nth root of A times the nth root of B is the nth root of the product AB. So number 18, applying this to number 18, tells me the fourth root of 5 times the fourth root of 2 is the fourth root of 5 times 2, which is the fourth root of 10. And I can't simplify that radical any further. The fifth root of 2 times the fifth root of 48 is the fifth root of 2 times 48, which is the fifth root of 96, which can be simplified to the fifth root of 32, since 32 is a perfect power 5, times the fifth root of 3, which is 2 times the fifth root of 3. The fifth root of 32 is 2. Now I look at number 20, the seventh root of x cubed times the sixth root of x, and I see that I cannot use the quotient rule for radicals here, or the product rule for radicals, because these radicals have different indices. Their index has to be the same for me to use the product rule. Alright, so in order to apply the product rule of radicals, the radicals have to have the same index. And we worked this problem. This was actually number 15. In order to simplify this, we had to convert to rational exponents. Let's take a look at that again. So here we see that problem simplified with the use of radical exponents. We cannot simplify it with the product rule for radicals. Number 21, we're going to work by multiplying the coefficients. And then we're going to multiply the radicals. And we're going to apply the product rule for radicals. So the cube root of 4y squared times the cube root of 16y is the cube root of 64y cubed. So we're going to go ahead and carry out the product. 3x cubed times 7x cubed is 21x to the 6. And that gets multiplied by the cube root of 64y cubed, which is a perfect cube. So 21x to the 6 is multiplied by the cube root of 64, which is 4, and the cube root of y cubed, which is y, to give 84 x to the 6y. So that's my final answer on that one. Now we can look at the quotient rule for radicals, which says if the nth root of a and the nth root of b are real numbers, and b isn't 0, since I can't divide by 0, then the nth root of a over b is the same as the nth root of a divided by the nth root of b. So you can divide first, which is what we're doing on the left here, and then apply the radical, or you can apply the radical first and then do the division, which is what the expression on the right is saying. So let's apply the quotient rule to number 22. So here it works to divide first. 162 divided by 9 is 18. X to the 7th divided by x to the negative 3rd, using the quotient rule for exponents, is x to the 7 minus negative 3. So this is the square root of 18 x to the 10th. Which can be simplified by writing this as the square root of 9x to the 10th. These are the perfect square factors of 18x to the 10th times the square root of 2, which is 3x to the 5th times the square root of 2. So that's my final answer on that one. Here, the problem number 24, this is written saying apply the radicals first, then divide. But it's actually easiest for us to divide first and then apply the radical. So we'll write it in that way. So 3 into 108 is 36, and I then apply the radical. And I see that the final answer here is 6. Okay, here I want to apply the fourth root to a quotient, but I realize it's going to be easier to apply the fourth root to the numerator first and then separately to the denominator. So I rewrite it where I've done that. And now the fourth root of 256 is 4. That 256 is actually 4 to the fourth. And now I'm going to simplify the numerator radical by writing it as the product of two fourth roots. The first fourth root is going to be the fourth root of perfect powers of 4. So I'll put all the perfect power of 4 factors in the first radical. 23 isn't a perfect fourth power, nor does it have any factors that are. X to the fifth can be written as x to the fourth times x. Y to the 31st can be written as y to the 28th times y cubed. Z to the 14th can be written as z to the 12th times z squared. So notice in a fourth root that simplified, only the powers of 1, 2, and 3 can remain. So let's apply the fourth root to x to the fourth to get x. Notice I'm multiplying these powers by 1/4 because a fourth root is a power of 1/4. 28 times 1/4 is 7, so I get y to the 7th when I apply the fourth root to y to the 28th. 1/4 times 12 is 3, so the fourth root of z to the 12th is z cubed. And then I recopy this radical that can't be simplified. And then I write this whole expression over my denominator of 4. For number 25, it certainly works best for me to do the division first. So the cube root is applied to negative 162m divided by 3 to the m minus 2. So this is the cube root. 3 into negative 162 is negative 54. M to the first divided by m to the negative 2 is m to the 1 minus negative 2, which is m cubed. So I'm going to rewrite this so that the perfect cube factors, negative 27 m cubed, are in my first radical, and the imperfect remaining factor, 2, is in my second cube root radical. And so this simplifies to negative 3m, cube root of negative 27 is negative 3, cube root of m cubed is m, and that gets multiplied times the cube root of 2.